Greetings and welcome back. Lesson number 2 on solutions. So yesterday we went over the front page of our note packet, and there are a few things I want to expand on with that. But I'm going to flip the page here. We've got a few summarized notes here. You're going to need your notebooks, though. We're going to take some notes in greater detail. But we were talking yesterday about types of solutions. Example of gases dissolved in liquid, like dissolved carbon dioxide in pop, soda pop, the fizz. Would be an example of a gas that dissolves in liquid, or dissolved oxygen in water. When a fish breathes, it's not breaking apart water into hydrogen and oxygen. There are O2 molecules in between the H2O molecules. Very low concentration, but that's what the fish breathe. Liquids with liquids we said were miscible. A tincture is an alcohol-based solution where the solvent is an alcohol, it's not water. We've talked about that one in the past. It's just vocab you should know. And most of us are familiar with when a solid dissolves into a liquid. Solubility rules, table F tells you what dissolves and what doesn't. We've been through that. Dissociation means breaking apart. So an example of a dissociation equation here we have NaCl solid going into water, breaking apart into sodium positive 1 ions aqueous and chloride negative 1 ions aqueous. They're dissociated and mobile ions. That's why it conducts electricity. So you'll find a bunch of dissociation equations at the bottom of table I. Hydrated ions are ions that are surrounded by water, and we've done the molecule ion attraction back in our bonding unit. Of course, we've got foul-mouthed Mickey over here. The oxygen side is the negative side of a water molecule. So your negative ion gets surrounded with the hydrogens facing in. Your positive ion gets surrounded with the oxygens facing in. Factors that affect the solubility, how much you can dissolve. Well, temperature is one of them. Pressure. If you're talking about gases, and pressure only affects gases, not liquids or solids. The nature of the solute and solvent, like dissolves like. Let's face it, oil is not going to dissolve very much in water. Factors which affect the rate of solution, well, the rate of dissolving. Temperature, pressure for gases, surface area, and stirring it around, agitation. So, before we get on to the next page, I want to clarify a few things. If we are taking a solvent, water, and we dissolve a little bit of solute, in this case, sugar, I can stir it around. We'll get rid of the white background. It's a white solute. If we pick it up on the wood better. It would appear as though all of that sugar has dissolved. Now, I didn't put very much sugar in there, but that solution is what we would describe as dilute. It's not very concentrated. There isn't very much sugar compared to the amount of water. As I add more sugar, I'm making the solution more concentrated. Now, as long as all of that sugar dissolves, I have a homogeneous mixture there. If I can get all of this sugar to dissolve, it's homogeneous. The sugar isn't going to settle out after it dissolves. It's not going to be sweeter at the top or sweeter at the bottom. It's going to be evenly distributed throughout the water. So all of our sugar dissolves. I still have a homogeneous mixture there. If I reach a point where I've dissolved as much as I possibly can, this is what you do with your Cheerios in the morning, right? I'm going to hit a point of saturation, where eventually, as much sugar as you could possibly dissolve into this water is going to dissolve. And that's all she wrote. There's no more. Well, under normal circumstances. Let's see if I've hit saturation yet. I don't think so. We've still got some solid there, but not much. I wonder if that'll dissolve. I must confess I used some warm water. Well, I still have a homogeneous, unsaturated solution. How about that 7th heaping teaspoon of sugar onto your Cheerios in the morning? It's delicious. So here we go. Have I maxed out yet? Have I saturated the solution? Maybe. Still got some solid down there. Let's see if it dissolves. Sure does. Not yet saturated. All right. Turns out sugar is pretty soluble in warm water. Oh, just for good measure. Okay. I think I've maxed out. We'll see. Maybe not. No, I think I have. Now you can see undissolved solute at the bottom of the beaker. This mixture is no longer homogeneous. The liquid is saturated with sugar. No more can dissolve. It's reached its maximum amount. Any extra sugar I put in there goes to the bottom, and there it is at the bottom in a big clump. So I have a heterogeneous mixture at this point in time. Okay, get the sugar out of the way. Let's talk a little bit about what's going on here. If you turn to table G in your reference tables, you'll see the horrible title, Solubility Curves at Standard Pressure. It should say solubility as a function of temperature. Always whatever you plot on Y is a function of what you plot on X. And you'll notice that solubility, they have grams of solute per 100 grams of water. Solubility is an intensive property. It's a ratio. How much solute per 100 grams of solvent? So it's a part-to-part expression in this case. And you can see that there are various substances on here, some with positive slopes and some with negative slopes. If I look at solubility as a function of temperature for any one of the given solutes, that line represents the maximum amount of solute you can put into that 100 grams of water. So this is grams of solute per 100 grams of water. And when I hit that line, that's it. The solution has maxed out. It can't dissolve anymore. We said the solution is saturated. If I'm underneath the line, I can dissolve more at any given temperature. If I'm here, I can keep moving up until I hit that line. So anywhere underneath the line, the solution is said to be unsaturated. And if I'm very sneaky about things, and we'll talk about this in a future lesson, I can somehow get solutions to go into the range above the line, dissolve more than you're supposed to be able to. In which case, I have a supersaturated solution, which is unstable and temporary. Okay, so saturated, unsaturated, supersaturated. Not to be confused with curves that might look radically different. Here, if I have solubility as a function of temperature and solubility as a function of temperature, if I'm here, I'm on the line, I'm saturated, but I'm not very high up on the y-axis. I would describe this solution as saturated but dilute. It's not a very strong solution. Whereas over here, if I'm up pretty high on the y-axis, I mean that's pretty high. I would describe this solution as unsaturated, but it's fairly concentrated. So saturated doesn't have to go together with concentrated. Unsaturated doesn't have to go with dilute. They're different terms. People ask, well, how far up the y-axis do you need to be? There's no set number. If you're down here, you have a dilute solution. If you're up here, you have a concentrated solution. There is no set thing. It's just how far up the y-axis did you want to call it. Okay, so that's something that these notes you want to you want to get these in your notebook on separate paper. It'll help you. All right. So that was page 2 of our note packet, and we had some additional stuff there. We'll be coming back to solubility curves. I have a whole other lesson on the solubility as a function of temperature and what the nature of the solute does there. But here's our saturated is on the line. Here's our supersaturated above the line. Here's our unsaturated beneath the line. Okay? When it's unsaturated, you can dissolve more solute. When it's saturated, it's maxed out. You can't dissolve anymore. And when it's supersaturated, it's very rare. You've got more solute dissolved than you should be able to at any given temperature. Okay? Dilute versus concentrated. Dilute means that you don't have a lot of solute relative to the solvent. Concentrated means, yeah, you've got a lot of solute relative to the solvent. Dilute but saturated. Concentrated but unsaturated. All right? I just kind of summarized the notes here. It's kind of small, so I'll give you a good shot of it there. We talked yesterday about molarity as one expression of concentration. We said molarity, which was given the abbreviation capital M, was moles of solute divided by liters of solution. So it was a part to whole expression. Molality, I know, silly word, molality gets little m. Once again, that's a hidden compound unit. Numerator's the same. Moles of solute. But in this case, you're going to go over kilograms of solvent. So molarity is moles of solute over a volume of solution, and molality is moles of solute over a mass of solvent. It's a part to other part representation. Similar, but not the same. To prepare 1 liter of 1.00 molar solution, you're going to use a volumetric flask. It's a round bottom flask. It's got a line scratched into it. It tells you when I hit that line, the bottom of the meniscus is there. That's exactly 1 liter. So you would, 1, add some water to the flask. 2, mass out number of grams that equals 1 mole of your solute. So you can't measure moles directly, you can measure mass directly. So you go to your balance, you use your GFM, you figure out, well, okay, if it's sodium hydroxide, we said was 40 grams per mole. You put your weighing boat on, you hit 0, you start dishing it in there until it hits 40.0. You say, I've got 1 mole there. Okay. Add your solute to the flask. Stir it around. Dissolve it. Then add the rest of the water. When you're done, the bottom of the meniscus will be even with that 1 liter mark, and you'll have exactly 1 mole dissolved in 1 liter of solution. Now that's for a molar solution. If you want a molal solution, a little bit different. You need 1 mole of your solute, and you need 1 kilogram of water. Well, it turns out a kilogram of water is a liter of water. If it's 1 gram per milliliter, it's 1 kilogram per liter, or a 5 factor of 1,000. So what would you do? Start out with exactly a full liter of pure water. Mass out 1 mole of solute. Got to use your GFM. Add it to the flask. Stir and dissolve. Note, the final volume, because you're adding stuff into your flask, will be greater than 1 liter. There's your 1 liter mark. You might be up here now. So you've got more than 1 liter of solution, even though it contains a kilogram of water. So they're similar, but not the same. So you've got molar, total volume 1 liter. Molal, well, you'd prepare more than 1 liter of solution because you started with a liter of water, which is a kilogram of water. Now, if ever we do test again, if ever, I'm sure we'll figure it out. Which is more concentrated? .0 molar or 1.0 molal. I'm going to let you think about that for a little bit. Get back to you in our next video.